Hello friends, welcome to my channel. Let's have a look at problem 938, range sum of BST. So this is a problem for today's daily challenge. In this video, we're going to share some solution formats based on traversal. Here we're going to use recursion. So first I'll read through the problem statement to digest the requirements, and then we do the analysis, and finally we share the code. First, let's look at the problem statement. Given the root node of a binary search tree and two integers low and high, return the sum of values of all nodes with a value in the inclusive range low and high. So in other words, if a node value is greater than or equal to low and less than or equal to high, so we are going to count it in the final sum. So in the example 1, so the low is 7 and the high is 15, right? So we can see 10, 15 is in this range and 7 is in this range. So we are going to return the sum of these three numbers, that is 32. So in the second example, so the low is 6 and the high is 10. So because of the high is 10, we do not need to examine the red subtree of the rooted at 15, right? So let's count this one. So we know that let's see, low is 6, so and high is 10. So here, let's see, 6, 7, and 10 are in the range. So we're going to return the sum of these three numbers. So that is 23. So the constraints for this problem are the following. First, the number of nodes in the tree is in the range bounded below by 1 and bounded above by 2 times 10 to the power 4. And the node value is in particular positive, right? And the low and the high is bounded in between 1 and 10 to the power 5. And all the node values are unique. So with that said, we can do the code. So for this problem, this is an easy problem as marked by Leetcode. So we're going to do traversal, and then we just need to add some filter condition. For example, when we do the traversal, we check if the node value is in between the given bounds, so low and high. If so, we count that. So that's the overall strategy. So here, because we are looking, so that strategy actually not applies not only to binary search tree, but also to the general binary tree, right? Or in general, a tree. So here we want to make a useful observation. So for binary search tree, due to the binary search property, so the in-order traversal, so this is a special kind of traversal, special order. So it can first visit the left subtree, and then the root, and then the right subtree recursively. So the in-order traversal gives us an increasing list, right? So with that said, I guess we can do the coding. But let me mention that we do not need to confine ourselves to in-order traversal. Any traversal will be fine if we just use filter. So let me first write a solution using recursion. So first, let's see if not root. So in this case, so we are going to return 0. So this is a stop condition or a base case for the recursion. And then if there is a non-null tree, so let me first initialize the result for a to accumulate, and then we're going to check if low, the root is in this range, right, as required by the problem. Then we're going to increment this root value. So this is one step. Once we've done this, so actually we can do the recursion for self calls. So self range sum. So let me change this to be the original function name. So then the argument will be root. So here we are looking at left subtree, right? So we can low and high. And then we are going to add the result for range sum or root right. So low and high. So this way, so we're going to return the result. So this is our first solution format, right? So actually this plays a role of filtering. So we are writing this solution in a recursive format, right? You can actually do this in a iterative format. It's not hard. So you can use all kinds of traversals like pre-order, in-order, post-order. Any order of traversal will be fine. So let's do a check first. Yeah, it passes all the test cases. So now let's copy this function signature, and I'll change this one to be v1. I would like to write another solution format. So still similar to this one, but we want to make it more like the in-order traversal, but we want to do some check. So this is the case. So if not root, still we just need to do the return, right? Return 0. So otherwise, what we're going to do is like this. So if high is less than root value. So in this case, because let's see, in this case, we just need to return the result for left subtree, right? So we're going to range the root left. And low and high. So otherwise, so if low is greater than root value, so we're going to do this, right? Self range sum root right and low and high. Otherwise, so what we're going to do is do something like this. So self, so call this on the root left, so low, high, and then adding the root value, right? Root value. So this one is the case that the root value is out of bound, right? So in this case, the root value is inbound, so in the range. So self range sum. So I'm going to do root right, low and high. So if you look at the last return, so we first do the left subtree, and then the root, and then the right subtree. So this is exactly in parallel to in-order traversal. So now I guess we can do a check, and then do the generic case check. So this is another solution format. So still we want to practice another one, still another one. So in this one, so what we're going to do is that, let me copy this function signature again. So I'm going to change this one to be version v2. So for this one, maybe it's more brute force, but it's good to know. So here we want to emphasize the connection of in-order traversal with the BST property. So first, I'm going to do an in-order traversal, and then I will save it as a list, and then we just pop out the ones out of range. So this is compared to the three versions, this is the most verbose one, but we want to demonstrate that. So here, let me define a hyperfunction. It's called root. So I do not care about the low and high at this stage. So we just need to return the in-order traversal result. So first, this is a stop condition or base case. So if not root, we're going to return an empty list. Otherwise, so we're going to do in-order root left and root value, and then plus in-order root right. So if you compare this return and then here, you can see, yeah, so that's in parallel to in-order traversal. So for this, I'm going to introduce a deck container. So here I can use collections deck. So I will make a deck out of the in order traversal result. So in order root, right? So then once we get this list, so because deck we can pop from left, we can pop from right, and then this is the case. We are going to pop out the values out of bound. So let's see, well, deck, and so let's see. What we want actually is deck. Let's first pop from the tail. So if this is in between the bound, so we're going to remain that. So we put a not here. So that is out of this bound. So we're going to do deck pop. So similarly, so we want to copy this one, and let's see that at the very beginning, right? So that is 0. So we're going to pop left. So this way we also practice the use of deck. So once we've done this, so what remains in the deck is the values that are in the range between low and high. So then we just need to return sum of the deck, right? So deck is an iterable, so we can do this directly. So this is another solution format, but this one logically it's very straightforward. But this more or both for this problem in some sense. So now let's do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So in here, so I wrote these things with a recursion to save some time. So if you like, you can write these solutions in an iterative format, right? So with that said, I guess that's about it for this specific problem. Thank you.